The Cafferty Group Technical Service Advisors, with locations in Nebraska, Iowa, Kansas, and Colorado, presents Essential HVAC Principles Training, Inverter Technology. In this training, we will cover inverter fundamentals, inverter components, inverter benefits, and the impact on comfort. What is an inverter? An inverter is a variable frequency drive that changes the electrical frequency and voltage applied to the compressor motor. Inverter drive technology is used to vary the HVAC system's operating capacity to match the heating or cooling load. The inverter drive controls compressor speed like a throttle controls an automobile engine speed. The inverter varies the applied frequency and voltage to the compressor based on a number of system temperature sensors and set points. Let's unravel the mystery. The incoming power enters the outdoor unit as 208 to 230 volt single-phase AC power. The incoming AC power is routed to the AC-DC rectifier circuit. The first component it comes in contact with is a group of diodes. A diode works like an electrical check valve. It allows electricity to flow in one direction and blocks that flow in the other direction. So the electricity will flow in the direction of the arrow, but is blocked in the opposite direction. So this would convert the incoming AC power to DC voltage. The red line indicates positive DC voltage. The light blue line indicates negative DC voltage, since the diode allows the power to flow toward the arrow and the ground to flow the opposite direction. The DC voltage then travels through the reactor. The reactor is a component that resembles a transformer, but the primary and secondary windings are the same size, so there is no change in voltage. Its function is to help clean up the power by removing white noise and harmonics and improve the power factor. The next component in the chain is a smoothing capacitor, or a series of smoothing capacitors. The smoothing capacitor stores electricity and discharges that electricity when there is a drop in the voltage. Since the incoming AC voltage is alternating directions 60 times per second, since the diodes only allow power to flow one direction, it will only send the upper side of the sine wave through the diode, which means there is a gap in the power 60 times per second. So the capacitor would discharge 60 times per second to fill those gaps and make that incoming DC power smooth. The DC voltage then enters the DC inverter that uses pulse width modulation to create a simulated AC sine wave at variable frequencies. The simulated AC sine wave is created by 6 insulated gate bipolar transistors, or IGBTs. The simulated AC voltage is used to operate the 3-phase AC compressor motor. This is done to give the system the ability to run that 3-phase compressor at not just 60 Hz, which 3-phase incoming AC would provide, but vary that frequency in order to vary the speed of the compressor. Inverter fundamentals. Imagine that your car only operated at a single speed, which would be like removing the accelerator and installing an on and off switch. Sometimes it would be traveling too fast for the conditions. Sometimes it would be traveling too slow for the conditions. Obviously, that would be a pretty inefficient way to travel. It's better to match your speed to the conditions, wouldn't you agree? Now imagine your air conditioner compressor operating at a single speed. Sometimes it would be moving too much refrigerant for the conditions, overspeeding. Sometimes it would be moving too little refrigerant for the conditions, underspeeding. Obviously, not a very efficient way to meet comfort needs. It's better to match the speed to the conditions, wouldn't you agree? So how do we match the compressor speed to meet the comfort needs? There are two ways to change the speed of a compressor motor. We could change the number of poles, so the motor speed would be equal to 120 times the frequency divided by the number of poles in the motor. So, that would be 120 times 60 cycles divided by 2 poles would be 3,600 RPM. 120 times 60 cycles divided by 4 poles would be 1,800 RPM. 120 times 60 cycles divided by 6 poles would be 1,200 RPM. Or, we could vary the electrical frequency and voltage being sent to the compressor motor. An inverter is a variable speed drive that does just that. But how does it do it? Simple. It rectifies AC into DC and inverts it back into AC. Here's how. Let's look at the rectifier component's functions first, then the inverter component functions. A diode, forward biased. An electronic switch. When the anode sees a positive sine wave, switch closes and allows current to flow. The rectifier is forward biased. Diode, reverse biased. An electronic switch. When the anode sees a negative sine wave, the switch opens and current flow stops. The rectifier is reverse biased. Half-wave rectification. The voltages at points A and B are changing in opposite directions. When A is increasing in a positive direction, B is increasing negatively. During the first half cycle, A is positive, B is negative. The diode has positive on its anode and negative on its cathode. During the next half cycle, A is negative and B is positive. The diode has negative on its anode and positive on its cathode. The diode is reverse biased. The load sees no current. Half of the cycle's current is unused. Full wave rectification. During the first half cycle, A is positive and B is negative. D1 has positive on its anode, D2 has negative on its cathode. Both diodes are forward biased. Load sees current. During the next half cycle, A is negative and B is positive. D4 has positive on its anode, D3 has negative on its cathode. Both are forward biased. Load sees current in the same direction. Now the entire cycle's sine wave current is used. Ripple. The rectifier circuit, through a system of diodes, converts the negative side of the AC sine wave to positive, although this is still not a smooth DC output and still contains peaks and valleys, or ripple. Eliminating ripple using capacitors and inductors. As voltage begins to decrease after each peak, the capacitor discharges and fills in the valley between the peaks. The result is a smooth DC voltage output. The inductor stores energy in its magnetic field and releases energy as needed in its attempt to maintain a constant current through itself. This helps to smooth out the ripple voltage. Let's look at the inverter component's functions. The insulated gate bipolar transistor, or IGBT, also referred to as a triac. Inverting the DC back to AC is accomplished with a transistor. This transistor is comprised of three elements: the collector from the DC bus or power into the IGBT, the emitter, output to the load, and the gate to control the switching frequency and output voltage. By varying the speed of the switching, the frequency of the AC output wave can be modulated, known as pulse width modulation, or PWM. Here is an example of a perfect AC sine wave. Here's an example of the pulse width modulation sine wave. The less time the power device remains on, the lower the output voltage. Equally, the longer the power device is off, the lower the output frequency. This is achieved by applying full power for a defined amount of time. The longer the power device remains on, the higher the output voltage. This is called pulse amplitude modulation. Here is a chart showing the IGBT carrier frequency pulse graph, or IGBT switching frequency. Here's an example of an inverter 60 Hz output. Here's an example of an inverter 30 Hz output. Output voltage control. This is a replicated voltage because the output section produces about 2,000 full voltage pulses per second, which are spaced to yield an instantaneous output that is an average of the duration of the pulse and the duration of its previous space. The instantaneous averages replicate the progression of voltage through a sine wave, with pulses further apart at the ends and closer together toward the middle. This is for conceptual purposes only. It will vary by the manufacturer. Carrier frequency is 2000 Hz. Output frequency control, 2000 Hz, pulses per cycle. Here is 1/2 cycle of 60 Hz, 8.33 milliseconds, and 1/2 cycle of 30 Hz, 16.66 milliseconds. This diagram illustrates output over time. PAM, or pulse amplitude modulation. The current does not follow the voltage exactly, and as you can see from the diagram below, the wave peaks quite sharply and then flattens out to zero at the baseline. This flat section makes the system inefficient. To correct this and increase the efficiency of the circuit, the PAM technology is applied to the rectifier circuit. The pulse amplitude is modulated using an insulated gate bipolar transistor, or IGBT, the same high-grade type that is used in the pulse width modulation of the inverted sine wave. Here is an example of a sine wave without pulse amplitude modulation and a sine wave with pulse amplitude modulation. Without pulse amplitude modulation, the efficiency of the circuit ranges from about 85 to 90%. By applying pulse amplitude modulation, the efficiency is increased to 99%. Including the smoothing capacitor, the resulting voltage waveform and current waveform is as shown. Notice how the sine wave on the oscilloscope mirrors a normal AC sine wave. Here are some of the benefits the inverter offers. Power factor near unity. high efficiency in part load conditions. Minimal locked rotor amps means less stress on the windings. No light flicker on compressor startup. System pressures increase gradually, reducing noise and stress on piping. Better dehumidification and fewer start-stop cycles. As room temperature nears set point, the capacity is automatically throttled down. This makes for a huge decrease in compressor energy consumption. Using the new formula for Hertz versus horsepower, we see that a 5 Hertz decrease in speed results in a 23% decrease in energy consumption. So what are the benefits to the inverter? Electronic control of the compressor under a wide variety of operating conditions. During high output ambient temperatures, the discharge gas temperature sensors identify high temperatures. Electronically reduces compressor speed to limit high side pressure and energy consumption. It reduces energy usage at peak conditions. It also provides great heat performance. It allows the compressor to increase speed during cold outdoor ambient conditions. It generates higher head pressure, discharge gas temperature, discharge air temperature. Attains the same heat output as competitive systems with electric booster heat, but doesn't use the extra energy. It improves performance throughout the entire run sequence. Longer run periods at lower capacities means better dehumidification. Fewer compressor starts means less wear and tear on the compressor, meaning longer compressor life. Lower compressor speeds equals higher system efficiency since the condenser coil surface remains large in relation to the reduced capacity. Higher efficiency equals lower electric bills. Customer advantage: improved comfort. Capacity matches the load by reducing on and off cycles and temperature swings. Starting performance is improved by ramping the speed up to match the load. The diagram below shows a non-inverter air conditioner versus an inverter air conditioner. Non-inverter air conditioner will cause overcooling, poor temperature control, and inefficient use of energy. An inverter-driven air conditioner has a minimum temperature fluctuation and efficient use of energy. Thank you for joining us for Essential HVAC Principles Training, TF30 Inverter Technology. If you have any questions or need more information, please contact the Cafferty Group Technical Service Advisors at one of these 12 locations.